So this is going to be chapter 14, ethers, epoxides, and thioethers. So the formula of ethers are RO, R prime, where R and R prime are alkyl or aryl. They can be symmetrical or unsymmetrical, in which either the R groups across the ether are the same, so you can have two of the same R's, or unsymmetrical, where you have one R and one R prime. Some examples of ether are shown here. Here's a diethyl ether, which is a symmetrical ether. Methylphenyl ether, which is an unsymmetrical ether. And here, this is a cyclic ether, and this is a symmetrical ether called tetrahydrofuran. In terms of structure and polarity, right, so there is a dipole. The dipole follows as such, where your methyl groups go to your oxygen, and from your oxygen goes to the electrons, and you have an overall dipole moment going in this direction. There's an angle of 110 degrees, and therefore it is bent in terms of molecular geometry. These are sp3 hybridides, and it's polar. For boiling points, they're similar to alkanes of comparable molecular weights. As an example, you have propane, which is similar molecular weight to dimethyl ether. Shown here are the boiling points. In the case of pentane, which has a molecular weight of 72, diethyl ether would be similar. Again, the boiling points are similar here. In terms of hydrogen bonding, there are good ethers cannot hydrogen bond with another ether, so they have lower boiling points than alcohol. Ether molecules can hydrogen bond with water and alcohol molecules, so they are hydrogen bond acceptors. So shown here is alcohol and ether, right? So ethers you can't do hydrogen bonding, alcohols you can, but ethers with alcohol you can do a hydrogen bond. They are great solvents in general, so here are different ethers used as solvents. They're used as solvents because they can dissolve nonpolar and polar substances, and they are unreactive towards strong bases. If we look at ion solvations with ethers, ethers can solvate cations, whereas the anion is not well solvated. Alcohol solvates both cations and anions. So unlike alcohols, ethers can only ether can only solvate cations, so they cannot solvate these small anions. If we look at ether complexes, so for example, in Grignard reagents, the complexation of an ether with a Grignard reagent stabilizes the reagent and helps keeps it in solution. So here are ethers. What it does is it complexes to the positive charge of the magnesium, stabilizing it. They're also good with electrophiles. The ether's non-bonding electrons stabilize the borane. So here's borane, and here it's forming it's forming a complex with the borane and stabilizing it again. Another type of example of ether are called crown ethers. Crown ethers are essentially ethers that are cyclic. They can complex metal cations in the center of the ring, as shown here. The size of the ether ring will determine which cation it can solvate better, and complexation by crown ethers often allows polar inorganic solvents to dissolve in polar organic solvents. So in terms of common names of ether, essentially you name the two alkyl groups attached to the oxygen and then add the word ether. You name the groups in alphabetical order, and if it's symmetrical, you use the prefix di for, if it's an alkyl, it'll be dialkyl. So here are examples. Here's diethyl, right, ether, or ethyl ether, or here is, this is a tert-butyl, this is a methyl group, so it would be tert-butyl, alphabetically, methyl ether, or methyl tert-butyl ether. So in terms of value pack names, we have to figure out which one belongs to the alkoxy and alkane. So the more complex alkyl groups is going to be the alkane name, and then the small group with the oxygen becomes an alkoxy group. So we have to find the longest chain again. Longest chain would be 1, 2, 3, right? That would be a propane. Right, at this propane group you have 2 methyl and then 2 methoxy propane. Here, this is easy. This is going to be the complex alkyl group, so this will be the cyclohexane. And over here it will be the methoxy group, so it's methoxycyclohexane. If you have cyclic ethers, or otherwise known as heterocycles, have oxygen as part of the ring. We already know epoxides from last semesters, or oxiranes. When it's 4-membered, it's called oxetanes. When it's 5-membered, it's called oxalanes. And if it's removed, the hydrogens are removed, then it's unsaturated. It's furans. If it's 6-membered, it's oxanes. Again, if you have 2 levels of unsaturation on either end, then symmetrical, it's pyranes. And these are dioxanes. In terms of epoxide nomenclature, you name starting the alkene and add oxide. So, for example, this would be cyclohexene in the presence of MCPBA, or peroxybenzoic acid. You generate the cyclohexene oxide, right? So this would be one way of naming epoxides. The other way is that the oxygen can be treated as a substituent, for example, epoxy, on the compound, and then you would number everything accordingly. So you'd find the parent chain. In this case, it's the cyclohexane. You number it so that the lowest substituent, in terms of the epoxide, is at the lowest number. So it would be 1, 2, 3, 4. So this would be 1, 2 epoxy, 4 methyl, and because the methyl group is in the back and the epoxide is going up, this would be trans, right, in front of it. So it would be trans 1, 2 epoxy, 4 methyl cyclohexane. As another example, you find the longest chain. This would be 1, 2, 3, 4, 5, 6, in which the epoxide is at the lowest substituent. So at the 2, 3 position, it would be 2, 3 epoxy. At the 4 position, it would be 4 methoxy, and the 2, 3 epoxy would be cis. So it'd be cis 2, 3 epoxy, 4 methoxyhexane. So in terms of epoxide nomenclature, 3-membered ring of oxirane is the parent, oxygen is 1, and the other carbons are 2, 3. Substituents are named in alphabetical order. Here's just a regular oxirane or epoxide, 1, 2 epoxyethane. Now in terms of nomenclature, here it goes, 1, 2, 3. We choose this to be 2 because there's more alkyl chains being substituted on it versus this being 1. So once we number it in this order, then it's 2, right, diethyl, 3 isopropyl oxirane. The other way to do this is to find the longest chain, right, as we had shown before. So it would be 1, 2, 3, 4, 5, 6. In this case, you'd have 2-methyl hexane, right, and there'd be 1, 2. So at the 3, 4 would be 3, 4 epoxy, right? 4 ethyl, 2 methylhexane. So that would be this. Here, again, in the convention as shown before, you'd have 1, 2, 3. Oops, sorry, 1, 2, 3, where the methoxy is at the 2 position and the methyl is at the 3 position. So this would be 2-methoxy, 3-methyloxyrane. Now, the methoxy group and the methyl group are trans to one another, so you'd add the trans in front. If we were to do this in terms of nomenclature, it would be 1, 2, 3, so it would be a propane. At the 1, 2 position where you have your epoxy, also at the 1 position it would be methoxy, so it would be 1, 2 epoxy, 1 methylpropane. In terms of synthesis of ethers, a common way to generate ethers are through Williamson ether synthesis. Here's an alkoxide, an alkyl halide. We're doing SN2 reaction, nucleophilic attack on the carbon center, expulsion of the leaving group, generating your ether, and then your halide. So this method involves SN2 attack of the alkoxide of an unhindered primary halide or tosylate. Alkoxide is commonly made by adding either sodium, potassium, or sodium hydride to the alcohol. Some examples of Williamson synthesis, right? So you're taking the alcohol, you can use sodium, right, or sodium hydride in this case. That'll generate, in step 1, the alkoxide. Then you're adding the alkyl halide or alkyl tosylate, shown here, to generate ethyl cyclohexane here, or here the 2-methoxy-3,3-dimethylpentane. Phenyl ethers, it's the same thing. In terms of phenyl ethers, you first have to generate the phenoxide. Phenoxide ions are easily produced because the alcohol proton is acidic, so since it's acidic, you don't even have to use the metals. You can just use a base, right? So sodium hydroxide will deprotonate that, furning the alkoxide, and then you add step 2, the alkyl halide. So phenyl halides or tosylates cannot be used. This is key. So for a synthesis method. So instead of using the phenyl part for the halides or the tosylate, you always deprotonate using a base to make the phenoxide ion. Keep that in mind. So let's do a problem. Why is the following reaction a poor method for the synthesis of tert-butyl propyl ether? So here's the synthesis of tert-butyl propyl ether. You're using the propoxide, then you're using tert-butyl bromide, and you're trying to generate the ether. So why is that bad? Well, it's bad because this is a tertiary alkyl halide instead of a primary alkyl halide. As a result, instead of doing SN2, what will happen, it'll deprotonate the proton here, forming an elimination, E2 elimination, generating isobutylene, the alcohol, and sodium bromide. So if we were to propose a better synthesis would be to generate the sodium tert-butoxide first, using the bromopropane as your alkyl halide, and then you're doing nucleophilic attack and SN2 reaction, leaving group leaves, generating your tert-butyl propyl ether. An important thing to note is that to convert 2 alcohols to an ether, always convert the more hindered alcohol to its alkoxide, and convert the less hindered alcohol to its tosylate or alkyl halide. Make sure that the tosylate or halide is a good SN2 substrate. Another way to make ethers is through alkoxymercuration, demercuration. You guys learned this last semester. You have an alkene. The first part or step of alkoxymercuration, demercuration is to add the mercuric acetate in the presence of alcohol. This will generate a mercurial ether, shown here, and then you can reduce it with sodium borohydride, where the ether portion remains, replace the mercury with the hydrogen. So for example, if we have hex-1-ene, right, if you reacted with HgOAc2 and CH3OH methanol and reduce second step with sodium borohydride, you generate the ether, right? Again, the OCH3, or the alkoxide portion of the ether, will go on the most substituted carbon, obeying Markovnikov rules. In terms of industrial synthesis of ethers, they use a bimolecular condensation of alcohols. It's an industrial method, therefore it's not a good lab synthesis. If the temperature is too high, alkenes are formed. So in industrial ether synthesis, you take, for example, 2-ethanol in the presence of acid at high temperatures, it'll generate the diethyl ether. So we're going to stop here for this portion.